Behind the Iron Curtain, innovation didn't come from laboratories or corporate budgets. It came from desperation. In the late 1960s, while Porsche engineers in Germany calculated limits on paper, a Polish farmer faced those limits in a muddy field and refused to accept them. Armed with scrap metal, intuition, and necessity, he challenged a machine that was never meant to be challenged. What followed wasn't just a mechanical modification, but a quiet rebellion against factory assumptions and economic control. This is the story of how scarcity, not luxury, produced an idea bold enough to embarrass Stuttgart and rewrite what impossible really meant. Scarcity breeds radical innovation. Picture this. It is 1968. You are standing in the middle of a muddy field in the Masovian plains of Poland. The wind is biting, the sky is a flat, industrial gray, and you are entirely alone. Behind you lies the Iron Curtain, a political and economic wall that separates you from the rest of the world. In front of you sits a tractor. It's not just any tractor, but a Porsche, a rare, air-cooled piece of German precision that somehow found its way into the depths of the Eastern Bloc. But there is a problem. The machine is beautiful, engineered by some of the finest minds in Stuttgart, yet it is failing. The heavy clay-rich soil of Poland is simply too much for it. The engine strains, the wheels slip, and the plow barely scratches the surface. In the People's Republic of Poland, or PRL, there is no dealership to call for an upgrade. The state-run collective farms, known as PGRs, hoard the modern equipment, leaving private farmers like you to scavenge for survival. You can apply for a new domestic tractor, but the waiting list is 5 years long. This is the reality for Stanislaw, a man known locally as the village genius. He doesn't see a broken machine, he sees a challenge. This environment gave rise to a cultural phenomenon known as Polak potrafi, meaning a Pole can do it. This wasn't a cheerful motivational poster on a workshop wall. It was a gritty, desperate survival strategy. It meant that if your equipment didn't work, you didn't eat. Stanislaw looked at that underpowered German engine and decided he wouldn't wait for the state to save him. Instead, he would use the very scarcity that imprisoned him to build something the original engineers said was impossible. He was about to turn a modest farm tractor into a turbocharged monster using scrap metal and sheer will. German precision meets thermal limits. To fully grasp the audacity of this modification, we must first appreciate the machine Stanislaw was working with. Ferdinand Porsche, the same mind behind the Volkswagen Beetle, applied his philosophy of the people's car to agriculture, creating the Volksschlepper, or people's tractor. These machines were triumphs of industrial minimalism. They were designed not just to work, but to last forever with minimal maintenance. The genius of the design was its modular architecture. Whether a farmer bought the small single-cylinder Junior 108 or the large four-cylinder Master 408, the underlying engineering remained identical. In this system, every cylinder was an independent island. Each one featured its own separate cylinder head, its own fuel injection circuit, and its own dedicated cooling fins. This made the tractor incredibly easy to repair. If one cylinder failed, you could fix it without dismantling the entire block. However, this design relied entirely on air cooling. Porsche engineers eliminated liquid cooling to remove the most common points of failure on a farm: the radiator, the water pump, and the rubber hoses. This reliability came with a strict physical cost governed by thermodynamics. While water is excellent at absorbing and moving heat, air is comparatively inefficient. The cooling capacity of these engines was determined by a convection equation, where heat transfer depends on the surface area of the metal fins and the speed of the air flowing over them. The factory engineers had calculated these variables down to the millimeter to handle exactly 38 horsepower, and not a single horse more. The surface area of the cooling fins was fixed. This created a hard thermal ceiling. Adding more power would generate heat that the physical geometry of the engine simply could not dissipate, threatening to melt the piston crowns and warp the heads. Vineyard engineering meets Masovian clay. The Porsche Super was an engineering marvel, but it was designed for the wrong world. Ferdinand Porsche envisioned these machines tiptoeing through the scenic vineyards of the Rhine Valley, prioritizing fuel efficiency and tight turning radii for light horticultural work. But Stanislaw wasn't farming grapes in Stuttgart. He was farming the Masovian plains of Poland. The soil here is heavy, moisture-laden clay with a cohesive strength that acts less like dirt and more like industrial glue. When Stanislaw hitched a standard 4-bottom plow to the Porsche, the mismatch was immediate and brutal. It was like trying to tow a fishing boat with a 10-speed bicycle. The 38-horsepower engine would roar, the wheels would fight for traction, but the torque simply wasn't there to shear through the dense earth. In a functional market economy, the solution would be to sell the tractor and buy a larger one. But in the 1960s Polish People's Republic, the market was broken. The state-allocated Ursus ED 325 SA, or the heavy-duty Zetor tractors from Czechoslovakia, were reserved for the collective farms. A private farmer like Stanislaw could put his name on a waiting list, but that meant watching 5 harvest seasons pass by, while waiting for a delivery that might never come. He was trapped between a machine that was too weak to feed his family, and a government that refused to sell him a better one. He realized that if he wanted the power of a heavy industrial tractor, he would have to manufacture it himself. Stanislaw needed forced induction, but there was no catalog for high-performance tractor parts behind the Iron Curtain. His only shopping mall was the local military surplus yard, a graveyard of decommissioned Soviet hardware. He wasn't looking for a refined, small-displacement turbocharger, because they simply didn't exist in his world. Instead, he scavenged a massive turbine unit ripped from the carcass of a heavy-duty Soviet truck, likely a Zeal 130 or a Star 28 series. This was not a plug-and-play modification. It was a collision of incompatible engineering scales. The Soviet turbo was designed for an engine with a displacement of 6 to 8 liters, operating at high tactical loads. Stanislaw was bolting it onto a 2.5-liter farm tractor. The size difference created a massive fluid dynamic challenge. The compressor and turbine wheels in the Soviet unit were heavy, built for durability rather than responsiveness. Water pipes become exhaust manifolds. The most daunting physical barrier Stanislaw faced wasn't the turbocharger itself, but the connection point. In modern automotive modification, you can order a machined steel flange with a standard T3 or T4 bolt pattern that perfectly mates a turbo to an exhaust manifold. In 1960s rural Poland, those standards did not exist. The exhaust ports on the Porsche diesel were designed for simple, low-velocity release, while the inlet on the massive Soviet turbine was designed for a heavy truck manifold. There was absolutely no way to bolt them together. Stanislaw's solution was a masterclass in agricultural improvisation. He didn't try to replicate a factory automotive manifold using thin sheet metal. Instead, he turned to plumbing. He scavenged heavy-gauge steel water pipes to fabricate a custom manifold. To the untrained eye, this looked crude, a mess of heavy, ugly piping welded together in a barn. But from a thermal engineering perspective, it was accidentally brilliant. Automotive exhaust manifolds are often made of cast iron or thin-walled stainless steel to save weight. However, thin metal has low thermal inertia. When you bolt a 20-kilogram Soviet turbocharger to a thin pipe and subject it to the intense vibration of a diesel engine, the metal fatigues and cracks. By using thick-walled water pipes, Stanislaw added necessary structural rigidity. These pipes were designed to hold high-pressure fluids, meaning their walls were thick enough to absorb the immense heat of exhaust gases, exceeding 600 degrees Celsius without warping or cracking. The fabrication process required immense patience. Using primitive arc welding equipment, he had to cut the pipes at precise angles to merge the exhaust from 3 separate cylinders into a single collector that matched the rectangular inlet of the Soviet turbine. The interior of the pipes likely created turbulence and back pressure that would horrify a Formula One engineer, but that didn't matter. The priority was durability. The thick steel provided a stable platform that could support the heavy, cantilevered mass of the turbocharger, effectively using the manifold as a structural bracket as well as a gas conduit. Cooling oil with car parts. By all known laws of engineering, this is the moment the project should have failed. The turbocharging an air-cooled engine is generally considered mechanical suicide. In a liquid-cooled engine, if you add more heat, you simply install a larger radiator or a high-flow water pump. But the Porsche diesel had no water to cool. It relied entirely on air, and the factory cooling fan was already working at its maximum capacity. With the turbocharger forcing more air and fuel into the cylinders, the combustion temperatures were skyrocketing. The immediate danger wasn't just melting the pistons, it was destroying the oil. In an engine like this, oil does double duty. It lubricates moving parts and cools the internal components that air can't reach. However, as oil gets hotter, it gets thinner. If the viscosity drops too low, the protective film between metal parts vanishes. For a turbocharger spinning at thousands of revolutions per minute, this is fatal. The moment the oil film breaks, the shaft grinds against the bearings, and the turbo seizes. Stanislaw needed a way to dump this excess heat, but he had no radiator. So, he built one. He scavenged a heater core from a scrapped automobile, essentially a small radiator designed to warm a car cabin. He realized that if he could route the tractor's hot oil through this core, it would act as a heat exchanger. He tapped into the Porsche's high-pressure oil galleries, plumbing the hot lubricant out of the engine and into the heater core. The brilliance was in the placement. He mounted this improvised oil cooler directly in the path of the tractor's existing axial cooling fan. As the engine RPM increased, the fan spun faster, pulling more air not just over the engine fins, but through his new oil cooler. He had effectively created a dynamic cooling system, where the cooling capacity increased in direct proportion to the engine load. This stopped the oil from cooking and kept the turbocharger spinning, preventing the thermal runaway that factory engineers feared. Filing down German precision. Forced induction is a balanced equation. The turbocharger provides the air, but the engine must provide the fuel. If you add massive amounts of oxygen without increasing the diesel supply, the engine will run lean, run hot, and destroy itself. The heart of the Porsche diesel was the Bosch mechanical injection pump. This was a piece of high-precision German instrumentation, built with tolerances measured in microns to deliver the exact amount of fuel required for 38 horsepower. In a modern workshop, modifying a pump like this requires a computerized test bench and laser calibration. Stanislaw had neither. He had a set of jeweler's files and a mechanical intuition that bordered on the supernatural. He disassembled the pump on his workbench and began to manually reshape the internal delivery valves. He didn't have data sheets, he simply understood the geometry of flow. By carefully filing away metal from the fuel control plungers and adjusting the tension on the governor springs, he tricked the pump into staying open longer. He was calibrating the engine by ear and by sight. The goal was to inject significantly more fuel than necessary for combustion, creating a rich mixture. In a diesel engine, this excess fuel doesn't just produce power, it acts as a coolant. The unburned diesel absorbs heat as it vaporizes in the cylinder, lowering the combustion temperature and protecting the piston crowns from melting under the turbo's pressure. The result was the tractor's signature black puff, a plume of soot that appeared whenever the turbo spooled up. To an observer, it looked like pollution. To Stanislaw, it was a visual confirmation that his improvised thermal management system was working, using diesel fuel itself to keep the German iron from turning into molten slag. Field testing the Franken Porsche. The first time Stanislaw turned the key, the soundscape of the Polish countryside changed. The familiar, rhythmic clatter-clatter of the air-cooled Porsche diesel was still there, but it was now overlaid with the high-pitched, metallic scream of a Soviet turbine spinning at 60,000 RPM. It was the auditory signature of two opposing engineering philosophies colliding, German precision rattling against Russian brute force. The performance gains were not subtle. Estimates suggest the tractor jumped from its factory rating of 38 horsepower to somewhere between 75 and 82 horsepower. That is a 100% increase in output, achieved in a barn with scrap metal. The ultimate validation came in the field. Stanislaw took the machine out to the same clay-heavy earth that had previously defeated it. With a four-bottom plow hitched to the back, he dropped the clutch. The tractor didn't stall. It didn't bog down. It tore through the dense Masovian clay as if it were loose sand. The turbocharger, once spooled, provided a surge of torque that the original Porsche engineers never accounted for. However, physics always demands a price. The weak link immediately revealed itself to be the clutch. The factory friction plate was designed for 38 horsepower, not 80. It slipped and smoked under the new load. Stanislaw, true to form, didn't order a new one. He relined the clutch disc with high-friction industrial material, likely scavenged from heavy mining equipment or a truck brake system, finally transferring the full power of his creation to the ground. Engineers confront the impossible machine. The legend of Stanislaw didn't stay buried in the Masovian clay. It traveled to the Poznan International Fair, the premier industrial exhibition of the Eastern Bloc. And, one of the few places where the Iron Curtain lifted enough for Western companies to inspect the competition. According to local accounts, a delegation of engineers from Porsche Diesel Motorenbau attended the fair, likely expecting to see primitive Soviet machinery or negotiate licensing deals. Instead, they were brought face to face with Stanislaw's creation. The scene was a collision of two worlds. On one side stood the German engineers in sharp suits, men who spent their days in Stuttgart calculating thermal loads with slide rules and drafting tables. On the other side sat a tractor covered in mud, welded water pipes, and a massive Soviet truck turbocharger. Their reaction was reportedly one of profound, bewildered silence. They had spent years determining that turbocharging these air-cooled engines was physically impossible. Their data proved the heads would warp, the cylinders would melt, and the oil would coke. Yet, here was a farmer who didn't have the data, didn't have the budget, and didn't know it was impossible. So, he simply did it. This encounter underscored the fundamental difference between Cold War engineering philosophies. Western engineering was about optimization, refining a design within the safety of a regulated market. Eastern engineering was about adaptation, forcing a machine to survive in a hostile reality of scarcity. The Porsche representatives looked at the Franken Porsche and saw a violation of every engineering rule they held dear. Stanislaw looked at them and likely wondered why it took them so long to figure out that a heater core and a little extra fuel were all they needed to rewrite the laws of thermodynamics. Engineers confront the impossible machine. The legend of Stanislaw didn't stay buried in the Masovian clay. It traveled to the Poznan International Fair, the premier industrial exhibition of the Eastern Bloc, and one of the few places where the Iron Curtain lifted enough for Western companies to inspect the competition. According to local accounts, a delegation of engineers from Porsche Diesel Motorenbau attended the fair, likely expecting to see primitive Soviet machinery or negotiate licensing deals. Instead, they were brought face to face with Stanislaw's creation. The scene was a collision of two worlds. On one side stood the German engineers in sharp suits, men who spent their days in Stuttgart calculating thermal loads with slide rules and drafting tables. On the other side sat a tractor covered in mud, welded water pipes, and a massive Soviet truck turbocharger. Their reaction was reportedly one of profound, bewildered silence. They had spent years determining that turbocharging these air-cooled engines was physically impossible. Their data proved the heads would warp, the cylinders would melt, and the oil would coke. Yet, here was a farmer who didn't have the data, didn't have the budget, and didn't know it was impossible, so he simply did it. This encounter underscored the fundamental difference between Cold War engineering philosophies. Western engineering was about optimization, refining a design within the safety of a regulated market. Eastern engineering was about adaptation, forcing a machine to survive in a hostile reality of scarcity. The Porsche representatives looked at the Franken Porsche and saw a violation of every engineering rule they held dear. Stanislaw looked at them and likely wondered why it took them so long to figure out that a heater core and a little extra fuel were all they needed to rewrite the laws of thermodynamics. Beating the American factory design. History books will tell you that the age of the turbocharged tractor began in America with the release of the Allis-Chalmers D19 in 1961. On paper, it was a revolutionary machine, marking the first time a major manufacturer sold a tractor with forced induction right off the dealership floor. However, looking back with modern engineering knowledge, that American machine was arguably less robust than the makeshift invention built by a Polish farmer in a barn. The Allis-Chalmers D19 utilized a water-cooled Buda Lanova diesel engine. While water cooling is generally superior for managing heat, the engine block used a single long cylinder head casting. When the turbocharger pressurized the cylinders, the immense heat and pressure caused the metal to expand. Because the head was one solid piece of iron, it had nowhere to go. This led to a plague of cracked cylinder heads and blown gaskets, as the internal stresses tore the engine apart. The factory engineers had bolted a turbo onto an engine architecture that was too rigid to handle it. Stanislaw, by contrast, had an accidental advantage. The Porsche diesel modular design, with its separate cylinder heads, acted like a series of expansion joints on a bridge. When the turbocharger heated the engine, each cylinder could expand and contract independently, without fighting its neighbors. Combined with Stanislaw's improvised oil cooling system, this meant the air-cooled improvised tractor was likely thermally more stable than the water-cooled American factory model. The Alice Chalmers engineers were trying to force a rigid system to accept boost, while Stanislaw allowed his machine to breathe and move with the heat. It turns out that sometimes a scavenged water pipe and a Soviet truck part outperform a multi-million-dollar research budget. The lost art of repair. The story of the turbocharged Porsche is more than just a mechanical curiosity. It is a monument to a vanishing form of literacy. In the modern world, we live in an era of disposable technology and proprietary software locks, where manufacturers treat owners as mere users. But in the People's Republic of Poland, the right to repair was not a legal concept debated in parliament. It was a physical reality dictated by survival. If a machine broke, there was no customer service number to call. You were the warranty. This environment produced a generation of mechanics who were not simply parts swappers. They were practical physicists who understood the first principles of thermodynamics and metallurgy. They did not view a tractor as a static, finished product delivered from a factory, but as a collection of mechanical possibilities waiting to be unlocked. Stanislaw's creation stands as the ultimate expression of this mindset. It proves that the engineering barriers cited by corporations are often just suggestions. When stripped of resources and backed into a corner, the human mind is capable of bypassing almost any limitation with enough desperation and a well-stocked scrap pile. Surviving the double torque load. The primary question surrounding this machine is how the drivetrain survived a 100% increase in output. The physics of torque transmission are unforgiving. By doubling the horsepower while maintaining the original engine speed, Stanislaw effectively doubled the shear stress applied to every gear tooth in the transmission. In a standard fatigue analysis, this level of overload should lead to specific failure modes. The first is gear tooth pitting, where localized pressure exceeds the yield strength of the steel, causing the surface to crumble. The second is bearing spalling, where the increased radial loads cause the metal races to flake apart. Finally, there is clutch glazing, where excessive heat crystallizes the friction material and destroys its ability to grip. Yet, this tractor remained operational for years. The secret to its longevity lay in the nature of agricultural work. Unlike a semi-truck hauling cargo on a highway, which subjects the drivetrain to constant high-load stress for hours, a tractor operates in bursts. It experiences peak torque only when the plow engages the earth, followed by periods of low load during turns or transport. This intermittent duty cycle allowed the oil to cool and the metal to recover between stress events. The Porsche transmission was built with a safety factor, but it was never intended to handle this magnitude of force. The survival of the machine relied on the operator acting as the torque limiter. Stanislaw acted as a biological sensor, operating the machine by feel and sensing the harmonic vibrations that precede failure. When the chassis shuddered or the gear wind changed pitch, he would back off the throttle. This symbiosis between man and machine allowed him to ride the edge of mechanical failure without ever crossing it, keeping the stress just below the fracture point of the German steel. The farmer outpaces the factory. Stanislaw's turbocharged Porsche diesel stands as a vital bridge between the experimental coal dust engines of the 1930s and the high-performance agricultural machinery of the modern era. While Porsche eventually abandoned the fields of Europe to focus on the high-speed racetracks that define the brand today, this modification remains a testament to their early legacy of utility. Stanislaw pushed the machine further than the engineers in Stuttgart ever dared to imagine. He proved that under the shadow of the Iron Curtain, a unique alchemy of German iron, Soviet air, and Polish ingenuity could achieve the impossible. This tractor did not just plow the heavy Masovian clay, it served as a mobile laboratory demonstrating the enduring power of human innovation. In the face of absolute scarcity, Stanislaw did not just maintain the machine, he evolved it. His work serves as a permanent reminder that the true limit of engineering is not found in a factory manual, but in the determination of the person holding the wrench. The factory built a tractor, but the farmer built a legend.